The biggest piece that you need to make sure you understand. So first of all, when we're talking about continuity, okay, a function f is considered to be continuous at a given point C if the following conditions are met. We need to find out where that belongs. Okay, so here, continuous at C, provided the following conditions. All right, so first of all, what we need to look at is, does the limit as x approaches C exist? And what you need to make sure of here is that you are evaluating the limit as x approaches C from the right of that function, and that it is equal to the limit as x approaches C from the left of that same function. So the left and right-handed limits have to exist, and they must be the same. Then in the next step, you need to make sure that f of C exists and that it falls within the domain of f. Okay? But the biggest piece here is this last one. So I'm going to use a different color. Here, the limit as x approaches C and f of C must be equal to each other. Meaning conditions number 1 and number 2 must be equal. So you need to make sure that the limit as x approaches C from both the left and the right is the same as f of C. Okay, so here's an example that we're going to go through, and we are actually going to go through the first part together, then you guys will do the second part, and then we'll go over it. So you're given the function as a piecewise, and then you're also given the graph. And a lot of times when you're given the graph, it's just easier to read the graph. It's the same thing. What we want to know here, does f of negative 1 exist? It's just a yes or no question, so I'll put a y for yes and an n for no. Does f of negative 1 exist? Yes, the point exists. It's right here. So we have a y here. Does the limit as x approaches negative 1 from the right exist? Yes. Okay. Does the limit as x approaches negative 1 from the right equal f of negative 1? Yes, it does. Okay, now go back and briefly read the definition and then think about, before you answer, is f of x continuous at x equals negative 1? I see a head shaking. Why? No. We have no idea what's happening from the left, right? Either the graph is incomplete, even in the piecewise function, we don't have that information, do we? So in this case, we cannot really answer that question. So for us to say that the function is continuous, we can't evaluate the limit as x approaches negative 1 from the left. So the answer here is no. Okay, you need to be able to evaluate the limit. So in this case, from both sides. So in this case, we can't even do that. So we can't really answer that question. So the answer has to be no. Okay, so I'm just going to give you just a minute or so to take a look at 5 through 8, and then we'll go over them together. Okay, and even blue. So we're going to take a look here. All right, and we are going to answer, does f of 1 exist? F of 1. Yes, it exists. Okay, does the limit as x approaches 1 exist? The limit itself. Yes or no? Yes, it exists. Okay. Are the limit and the point equal to each other? No, they are not. So is the function continuous at x equals 1? No. So if you had to justify your answer here, you would have to basically show me that the limit as x approaches 1 from the left is equal to 2, which is equal to the limit as x approaches 1 from the right. That's a true statement, correct? I'm just basically sandwiching the limit between the two. Then you would have to state that f of 1 is equal to 1, which is not equal to the limit. That's your justification. You don't have to give a verbal. You could write it all in mathematical terms. Okay, does anyone have any questions about that example and the definition of continuity? That's the biggest piece. Because if you're asked to determine if a function is continuous at a given point, you can't just say yes or no. You have to justify why it is or is not. And that's when you take the limit as x approaches c from the left, the limit as x approaches c from the right, as well as evaluate f of c. Those are the biggest pieces. Okay? All right, let's take a look at the next part. So here we have discontinuity. So if you have a function that has a discontinuity or a type of discontinuity, we have two categories, and then under non-removable discontinuities, we have two subcategories. So a function is considered discontinuous at x equals c given the following situations. So first of all, if we have a removable discontinuity, we're going to abbreviate that as RD. When you have a removable discontinuity, basically what you have is a hole at x equals c. So basically what we're saying here is that the limit as x approaches c from the right is equal to the left, but not equal to f of c. So you're given one graphic scenario here, okay, which is similar to what we had in the example, meaning your limit is the same and then your point is some other given value. But you could also have a graphic scenario here in which your limit exists, right? So we have the limit as x approaches c of f of x exists, we'll say, whatever that value is, but f of c does not exist. There is no point there at this given value c right here. Does that make sense? Okay, so it's just a possibility. Anything could happen. Then we have what's called a non-removable discontinuity, ND. All right, and we have two subcategories. We have a jump, which clearly is exactly what it looks like, and then your infinite discontinuity. All right, so here, a jump discontinuity, basically the left and right-handed limits are not equal to each other. And there could be so many different scenarios, but basically what you have here is, and you cannot use this as justification, but it's just a simplistic way of saying it, when you are sketching this graph, you literally have to jump from this point to the next one. Okay? So you could have a graph that looks like this. You could have a graph that looks like this. Yeah, you do. You could have a graph that looks like this. And I'm just making, these are just ridiculous graphs, but okay, these are all just possible scenarios. But either way, you have a jump in here. F of c might not even exist. Here we have f of c. Here you have f of c. Here you don't have one. Okay, but either way, the limits are not the same. Okay, in this last piece, an infinite discontinuity is basically when you have a vertical asymptote in the graph. Okay, and your graph will go infinitely in one direction versus the other. Okay, I think there was one question in those cards where I was talking about, I think it was -1 over x minus 1 squared or something like that. Or 1, I can't remember. But either way, you had to look at the end behavior from the left and from the right because you had a vertical asymptote at 1. And I gave another scenario if the signs were opposite, meaning on the right side you got a negative and on the left side you got a positive. You would have something like this. At that vertical asymptote, your graphs are going in different directions, so then the limit wouldn't exist. Okay? All right, questions on this first part before we apply? Everybody okay? All right.